come through now. So the end of the semester, right? Our last day of class is, well, for us it'll be Friday, right? Because next week we have just the assessment periods for the A days. Our assessment period is on Tuesday. And what we'll do there during the assessment period is I'm going to give you guys the option of taking the Chapter 6 test during that time. It's not required that you take the Chapter 6 test, but if you're sitting on a borderline grade or you're unhappy with where your grade is and you feel like I need another opportunity to get my test score up or whatever, that's an option for you. So that is there. We'll do that. So I think that some people were emailing me about possibly being out of town or this thing or that thing. So like, you just can take it or not. If it's easier to just not have to worry about it because you're happy with where your grade is, then there's nothing really to worry about there. We're still going to do one more homework quiz here before the end of the semester. I've already entered that into the grade book and marked it as missing because I also entered in a drop for a low homework quiz score. So right now what's being dropped is the missing assignment, which is not doing anything. But when we take that final homework quiz, presuming you do better there than somewhere else, it'll move that drop to now your lowest homework quiz score. So your low homework quiz score is going to be dropped. Right now it doesn't look like anything's happening because I have a missing entered in for this last homework quiz. But once that score goes in, once we take it, that drop will move to wherever it is that your low score is. I also dropped a low assignment. So if you have a missing or low or graded down assignment that was incomplete or whatever that hasn't been made up yet, you don't have to really worry about that. The low homework grade will be dropped. So your single low homework assignment will be dropped also. And I put in I doubled your high test score. So your best test grade I've put in twice. Now if you elect to do the Chapter 6 test and you do better on that, then whatever's in there, I'll update it also. But pretty much you guys are, if like you didn't do anything else for the rest of the semester, your number where your grade is right now is where your grade will finish. Like you can't do worse than where you're at right now. We will have one final homework check on, I've scheduled it for Tuesday at 8 a.m. as the final deadline to get it in, since B Day has one class period next week on Monday, so it seemed like just make the final homework check for that Tuesday morning or whatever. That way I don't have one homework check for you guys and two for the B class. And I've already made that assignment in PowerSchool and marked it as missing also, so the low homework score drop is being occupied there. If you do that, then obviously it'll move to whatever your new low homework is. So that's basically where we're at here for the last week. We're going to do Chapter 6. And once we're finished with Chapter 6, on the assessment period, you can elect to take the Chapter 6 test or not. It's not required. We'll do a homework quiz during the course of this week. And we'll have one final homework check for this Chapter 6 assignments. Again, if you know what's being dropped now, or where the drops are, basically if you did nothing more for the end of the semester, this is where your score is, so nothing would change. You can't get worse for not doing anything. Now, please, for the love of God, like, try to do some stuff and learn these last topics in Chapter 6, even if you're like, yeah, I'm good. Like, this is stuff that's still going to be important. It'll come up second semester. It'll come up in calculus next year if you elect to take calculus. Like, you'll want to have seen this material before, but there's not really a grade attached to it, so, like, you don't have to, like, you know, like, put it as the highest priority. But please do the assignments and do the work in good faith, and just worry about trying to understand and learn what's going on, and maybe not worry about the number so much maybe for this last week if you're happy with where you're at in the course.
Mr. Coolidge?
Yes.
So when you drop the lowest homework assignment, did you already do it?
So the computer does this automatically for me when I tell it to do it. I put that in already, but I also put in a missing for the final homework check.
Okay.
So, like, right now...
Does that count the count the homework from... Sorry. You can go.
Right now, the drop is most likely being applied to your missing final homework check, unless you have a missing somewhere earlier in the grade book. So, like, that's what's, like, that's where it's going on. Like, again, you can't do worse than your score is right now. It can only go up. Well, I guess it could get worse also if you took the Chapter 6 test and did badly. Like, if you do bad and it hurts you, I'm still putting it in. But does that answer your question, Dan?
Yeah, it does. Thank you.
Okay, no problem. Does anybody else have questions about what's going on with the end of the semester here? Okay, that's good. If something comes up and you're curious and you want and you have some more questions, feel free to ask. But I think all of that is pretty generous in terms of opportunities to kind of help yourself out and help your grade out a little bit. So I did a bunch of things there. Like the high test score is in already. The drops are set to happen already. They're being occupied by the missings this week, but presuming that you continue to do things, that'll continue to get better. Okay, so this week, Chapter 6. Is more identities. So this is talking about the sum, difference, and multiple angle identities.
Mr. Coolidge, can you share your screen?
Yep. Yeah, no, I knew that. Thank you. Thank you. I appreciate you guys saying something before I got too far along there and really became a giant hassle to fix that. And you guys got all very far behind. Okay. So what we're going to do is we're going to start by deriving our first of these identities, and then we'll use that identity to kind of cleverly generate the other ones. So the first derivation is going to be the most complicated because it's going to be from first principles. It's not something I'd ever ask you to repeat, but I think it's important that you guys can see and follow these kind of arguments. So we're going to start with a picture. So here is my angled rotation setup. And I'm going to draw in this angle, and then this angle here. So we're going to call this angle angle V, and we're going to call this angle angle U, which means that this angle here, that I'll call theta, is equal to U minus V. So I know that if we're talking about the unit, this point here that I'll call B is the point cosine V, comma sine V. And this point here that I'll call A is sine U, cosine U, comma sine U. Now, if I translate this, I can take this angle, angle theta, and I could just draw it in the first quadrant by like picking it up and like rotating it or whatever, but it's still going to be the same size angle. So I'm going to call this point A prime, which is cosine theta sine theta. This point B prime, which is just 1, 0. So what we're going to compare now is these two segments. And I know those two segments are equal because the triangles formed between the points A, B in the origin and A prime, B prime in the origin are congruent triangles, since the length of or the center, or the angle is theta, and the length of the two legs are both 1 because they're both intersecting, they're both radii of a unit circle. So I know that these two segments are congruent by angle side angle. Well, it's really corresponding parts of congruent triangles are congruent, but we know that triangles are congruent by angle side angle. And I'm going to use this relationship to derive a difference of two angles identity. Okay. So the length of AB I can calculate using the distance formula, right? So the distance formula would be the difference in the B coord, or the X coordinate for B and the X coordinate for A squared, plus the Y coordinate for B and the Y coordinate for A squared, all square rooted. And similarly over here, And, well, let's make our lives a little bit easier. And I'm going to square both sides to get rid of those pesky square roots.
Hey, Mr. Cooley.
Yes.
Where'd you get bx minus ax minus a squared?
That's the distance formula. So bx is the x-coordinate for the point B. And ax is the x-coordinate for...
Okay.
So it's just literally the distance
And
formula.
by is y.
Exactly.
Yeah, by is y and ay is y.
Yep. Yep. Exactly. So if I go and I look now at my points A and B, the x-coordinate for B is cosine V, and the y-coordinate for, or the x-coordinate for A is cosine U. So let's go ahead and substitute those in. And similarly, the y-coordinates are sines. B was 1. And then cosine theta. And then 0 sine theta. Again, the x-coordinate for B is 1, and the x-coordinate for A is cosine theta. Similarly, the y-coordinates. Okay. So now I'm going to go ahead and FOIL all of these out.
Got to go.
Bye. Try to make those V's pointier for you guys.
Can you scroll up a little bit, Mr. Cooley? Okay, I just wanted to make sure that was the step you followed.
Okay. And at this point, you're probably thinking, oh, dear me, what is going on? This looks pretty terrible. Well, it's about to get a lot less terrible. So I have a cosine squared V and a sine squared V. I know that I have a cosine squared U and a sine squared U. I know that gives me 1. And I have a cosine squared theta. So I know that's going to give me 1. I still have minus 2 cosine V cosine U and a minus 2 sine V sine U. I'm going to factor the negative 2 out and write it this way, though. And now I notice that I have, if I subtract 1 from both sides, those ones would cancel. If I subtract another 1 from both sides, those ones will cancel. And if I divide both sides by 2, those might, or divide by -2, both of those -2's are going to cancel. So I'm left with cosine v times cosine u plus sine v times sine u is equal to cosine theta. But if we remember way back to the very beginning, we said that theta is equal to u minus v. So let's go ahead and substitute that in. And there we go. That's our first identity for the difference of two angles. Sweet. If you look at the content library, you'll see that I made a new trig identity sheet on it that has the identities from the first chapter without the reciprocal or tangent, cotangent, or quotient identities. I took those off to make room for these new identities that we're going to see here in the next class or two.
You go up, Mr. Claude.
Well, I didn't.
Wherever.
I just was pointing out something. I'm going back. Now, what if I wanted to get the identity for cosine of u plus theta? Well, I can derive this. V is the same thing as u minus a negative v. Use the identity that I just created. And then using my odd-even identities from the previous chapter, I know cosine of negative v is just cosine of v. And I know cosine or sine of negative v is negative sine v. And that quickly gives me a new identity for the sum, or the cosine of the sum of two angles. Now, typically, we write these together in one statement. So cosine of u plus or minus v is equal to cosine of u times cosine of v minus plus sine u. So notice the way you read this is if you want u plus v, you're going to take the sign on the top, which is what we have here. Or if you wanted u minus v, you'll take the sign on the bottom, which is what we have here. So all that is, that statement with the plus and minuses in it, and the minus plus in it, is just a clever way of rewriting or combining these two statements into a single statement, just for compactness sake. You know, mathematicians are inherently lazy. If we can write it with one statement instead of two statements, boy, we love that. I know. Okay. So one of the things that you'll be asked to do using these identities is, or one of the main purposes we can use these identities for, is it allows us to find the exact values of angles that are not necessarily on the unit circle. So let's say we want to find the exact value of cosine of 75 degrees. Well, here's the trick, is I need to rewrite 75 as either or the difference of two angles that appear on the unit circle. So I'll think about that for a second and go, 75 is the same as 30 plus 45. Both of those are unit circle angles. That's what I'm going to... Were there other possibilities? Oh yeah, sure. I mean, you could have done like, 215 and 145, is that? No, 210 and 135 would be an example, but there's lots of them. This is just an example. So if I use my identity, then I'm going to be using the yellow one here because we have a sum. So this is going to turn into the cosine of 30 times the cosine of 45 minus the sine of 30 times the sine of 45. And then if I go to my unit circle, I can look up these values. So the cosine of 30 is root 3 over 2, and the sine of 30 is 1/2. And if I go to the unit circle, the cosine of 45 is square root 2 over 2. And the sine of 45 is square root 2 over 2. And if I multiply these fractions, square root 3 times square root 2 is square root 6. And 2 times 2 is 4. And 1 times the square root of 2 is the square root of 2. And 2 times 2 is 4. So the value of cosine of 75 is the square root of 6 minus the square root of 2, all divided by 4. Yeah.
How can you like subtract them from each other? Because I thought since it's like 30 plus 45, then you like add both of them.
So the plus has a subtraction. Right? That's what you're asking?
Yeah, okay, I got it.
Did you write down the identity wrong? That would be a bummer.
Yeah, I was just looking at like the other equation that you like combined, and then I just got confused.
Oh, yeah, you just have to look at it. Whatever's on top goes together, whatever's on bottom goes together. Does that make sense when I say that, top and bottom?
Yeah.
Okay. So that's nifty. We can now use what we know to do this now for sine. So rather than starting from first principles again and have to go through that whole big derivation, I'm just going to use identities to get what we want here. Oops. I'm going to write that the other way.
Mr. Cool, what does the U and V stand for? Are those the angles?
Those are angles, exactly. Yep.
So, original top angle where you gave us all 3 angles or what, or so. That's like a, you do all these problems based off of that?
No, I used that to generate my identity. That was just a derivation. So
that
angle.
big long thing, identity?
So the identities are what we boxed back here.
Okay, got it.
That whole lead up to it was the derivation of how we got there.
Right. All 3 of them are identities?
Well, this one is just the same as the other 2. It's just combined into a single statement.
Right.
So it's not like a new one. It's the same as the other 2. It's just written as one statement instead of 2.
Yeah, so we can use that instead of both of them. Okay.
Yeah.
And this is like the next step of the same problem, same example.
So what we came up with a sum and difference identity for cosine. We're going to now extend this to do sines. Right? So we want a sum and difference identity for sine.
Could you repeat that?
We have 2 identities. We have a sum or a difference identity for cosine and a sum identity for cosine.
Right.
We want to do the same thing now for sines.
Okay.
So I'm going to use this identity that sine is the same thing, pi over 2 minus theta. And then I'm going to use my cosine, or difference of angles for cosine. Oh, shoot. I don't want to do this yet. Sorry, that wasn't going to... I want to do something else before I do that. That. And this is the sneaky part that maybe wouldn't be obvious to do. Is I'm going to think about my 2 angles now as pi over 2 minus u and then v. The reason I wanted to do that is so that when I apply my difference of angles formula for cosine, it separates the u and v into their own separate trig functions. So now I can use my cofunction identity here. Cosine of pi over 2 minus u is the same as sine u. And sine of pi over 2 minus u is cosine u. So we have that. And we could do the same thing by writing that as with subtractions. I'm going to skip that and just go straight to the compact version. So we're going to start skipping some of these derivations in the interest of time. Again, I would never ask you to repeat any of these derivations for me on a test or a quiz or something. They're just part of being a good math student, is you're able to kind of follow these kinds of arguments. So again, here's the compact statement. Again, with the double plus or minuses like this, you read it as the sum identity you add, and the difference identity you would subtract.
Top box is sum, right?
Mm-hmm. That's correct.
So in the problems, are you trying to find the sum identity, or that's just the identity, right?
Yeah, this is just identities. We haven't. This is now.
Right,
This is an
touched
example
on it,
problem. Yeah.
Yeah.
So here in the example, we're asked to find the exact value of 5 pi over 12, which you'll notice is not a unit circle problem or a unit circle angle. What I want to do is I want to figure out a way to rewrite 5 pi over 12 as unit circle angles. Well, one way that's probably the easier to do this is to convert this into degrees. So 5 pi over 12 is 75 degrees, which I can think of as 45 and 30.
How'd you get 75?
I multiplied this by pi over, or 180 over pi. That's my conversion to go from radians to degrees.
You said 180 over pi?
Mm-hmm. Yep, that's like a chapter 1 thing. And then if I go to look at my unit circle, I know that 45 is the same thing as pi over 4. And 30 is the same thing as pi over 6. So I can do the sine of pi over 4 plus pi over 6, which gives me sine of pi over 4 times the cosine of pi over 6 plus the cosine of pi over 4 times the sine of pi over 6. If I go to my unit circle, the sine of pi over 4 is root 2 over 2. The cosine of pi over 6 is square root 3 over 2. The cosine of pi over 4 is square root 2 over 2. The sine of pi over 6 is 1/2. And once again, I get that square root of That's going to be a typo.
Damn, it's a cool. What are these identities called? Like on the identity sheet?
Sum and difference.
Okay.
Yeah, that's fine.
Well, in order to get the radical from 75, you have to see what degrees add up to 75 and then look at the radicals.
Yeah.
So it could have been like... So it could be any number, any degree adding up to 75 on a unit circle.
Correct. Or subtracting to 75.
Or subtracting, okay.
All right. So we're going to skip the derivation here. We're just going to write down the value. So we've seen we can use these sum and difference identities to find the exact values of sine, cosine, and tangent for angles that aren't necessarily on the unit circle. Not any angle, but some angles that are not on the unit circle, presuming that we can break that angle down into the sum or difference of two unit circle angles. What we can also do is if we have something like this, we notice that this is in the same form as the tangent identity up here. So we notice that we have a plus sign here. We have a minus sign here, so we need the one that's on top. So we can say this is just equal to tangent of, well, my u is 30, and my v is 26. So it's u, which is 30, plus v, which is 26. So this is just the tangent of 56. another thing we can do is we can use these to verify some identities. So let's suppose we want to prove that sine of x minus pi is equal to negative sine x. I would work on the side where I have the obvious sum or difference identity that I can apply, which in this case would be the left-hand side. And I would apply the sine angle, or the sine identity for the difference of two angles. So doing that, I get sine of x times cosine pi minus cosine of x sine of pi. If I go to my unit circle, cosine of pi and sine of pi are both things that I can evaluate. Cosine of pi is -1, and sine of pi is 0, which just turns into negative sine x, which is what we wanted. Let's do one that's a little bit trickier. So here I have cosine 3x plus cosine x equals 2 cosine 2x times cosine x. So both on the left hand side and on the right hand side I have potential identities that I could use. I would work on the left hand side because the 3x identity is like a bigger angle than the 2x is. And I'm just going to think of 3x as 2x plus x. I can then use my sum of two angles identity for cosine. Oops. So I notice now that I have part of that, right? I have one of those. I need another one somewhere. Right? So here's the sneaky part. I'm going to get this guy. And you're going to look at me and go, how in the world, Mr. Kulik, are you going to do that? That's just a cosine x. What angle, or what of these double angle identities could you possibly do? Or one of these sum or difference identities could you possibly do? Well, x is just 2x minus x, right? Oh, Mr. Kulik. I underestimated the sneakiness. I know you did. I know you did. So if I apply my difference of two angles for cosine, get cosine 2x times cosine x plus sine 2x sine x. And boom, boom, those cancel. Righteous. And these guys can add because they're like terms. And there is my ending spot.
Mr. Cooley,
Yeah.
did you do like a difference identity there or something? Or did you
Yep.
do angle identity?
Yeah.
Which one?
I did a sum here. Actually, let's...
Yeah.
And then I did a difference there.
The sum identity is the cos, and the difference identity.
Uh-huh. They're both cosines.
Well, I mean, like, oh, never mind. Do you have to strictly use the new identities, or can you use some of the old ones?
Well, the old ones I don't think would have been very helpful in this problem because we have these 2x's and 3x's rolling around.
But you could use the old ones in the future.
Yeah. Oh, yeah. It's not like they're wrong. I just don't think they were going to be helpful in this problem.
Yeah.
Okay. This previous one gives rise to some quite useful identities called the double angle identities. And I'm not going to derive these. I'm just going to list them. The derivations, though, would be quite straightforward. You just pick u and v to be the same thing. So just do like the sine of u plus u. Would simplify to this. Cosine of 2u is a little bit trickier to use because there's 3 versions of this. Oops. Forgot my u there. Okay, and then one more set for today are called the power reducing. And these just allow us to relate our double angle identities back to a single trig function, although the single trig function is a squared. So let's say, for example, I wanted to find the exact value of cosine squared of 60 degrees. Well, I can use my power reducing identity above to do that. And 2 times 60 is 120. And if I go to my unit circle, the cosine of 120 is -1/2. 1 plus -1/2 is 2. And 1/2 divided by 2 is 1/4. We can also do things that are a little bit sneakier, like cotangent squared of -165. So remember that cotangent is the reciprocal of tangent. And then using that, that's going to give me 1 plus cosine of 2 times -165, and 1 minus cosine 2 times -165. Notice that I flipped this fraction because I had 1 over tan squared, so I made the reciprocal. 165 times 2 is 330. If I go to my unit circle, cosine of 330 is that root 3 over 2, I think? Let me double check. Yeah.
Wait, Mr. Kulik,
Yes.
does it matter if it's like positive or negative 330, or do you just look for
Oh.
330?
Well, in this case, it won't because you're in quadrant 1. But yes, that's a good point. It is -330. So really, we're looking at cosine of 30 degrees.
Okay.
But yes, that's a good point. I got lucky because we were in the same quadrant either way. So we have that. And I'm going to get rid of this fraction in a fraction thing that's going on here by just multiplying the top and bottom by 2 over 2. It's definitely okay to do that, right? Because all I did was really multiply by 1. And then we don't like to have square roots in the denominator here. And it's a little bit trickier to handle this because I can't just multiply the top and bottom by square root of 3 because it'll just distribute and get stuck onto the 2. I need to multiply the top and bottom by the conjugate, which is 2 plus the square root of 3. So when I FOIL the top part out, I get 4 plus 2 root 3 plus 2 root 3 plus 3. And the bottom I get 2 minus 3. Or just 7 minus 4 root 3. And one last example for today, and we'll be done. So let's say we want to prove that sine cubed is equal to 1/2 sine x times 1 minus cosine 2x. Well, there's kind of two different approaches you could take with this. You could, one, use your double angle identities on the right, or the second, you could use your power reducing identities on the left. Either would be fine. I'm going to work on the left side and use the power reducing identities because I think it's going to be a little bit quicker, but it wouldn't really matter. You could do it either way. I'm going to begin by rewriting sine cubed as just sine x times sine squared. If I go to my power reducing identities, then sine squared is 1 minus cosine 2x all over 2. And then I can just take this 1/2 here and stick it on the sine, and I got what I needed. And that was pretty convenient. Okay, let's stop here. So the assignment for this week, we have the problems in the problem set. So right now you should be able to do like 1 through 20. I think we've done enough to do those. And you could probably do some of these on 35 to 40. I think we have done enough to do those as well. I'll write that down in a minute. I have worksheet 1, which you should definitely be able to do. At least the first 2 pages of. We haven't done the half angle identities yet. And then I put the review packet on here. Unless you're going to take the Chapter 6 test, I don't see any reason that you need to do the review packet if you did all that other work already. So I'm not going to assign this as something that's going to be due and collected. I'm just going to leave it as an option for the people that are going to elect to take the Chapter 6 test to work on. But I have put the key up for the review already. So, oops. Today we had done enough. Oops, that's the wrong day. We had done enough to get through 1 through 20 and then 35 to 40. And we will continue on with this chapter tomorrow.